Okay. So thank you, Cyril, for organizing this and inviting me. So as Boy said, I will do mostly like the part that is about stochastic stuff. Except that maybe for today I wanted to start maybe slowly. So for today it will be mostly generalities on functional inequalities and not so much of stochastic business. So I want to start with something that I will call Chigger's inequality. So what is this inequality? So the context. So mu is a probability measure on Rn. Or maybe at this stage it could be like a more general situation, or on some metric measure space. And what is the isoperimetric problem? So, the question is this. So given, so maybe among sets of fixed measure, which sets minimize the perimeter, minimize the perimeter. Okay, so we have to agree on what is the perimeter. So there are several possible notions of perimeter. So for the purpose of this talk, I will only consider what's called sometimes the Minkowski content. So given a subset of Rn or of the ambient space X, I will call mu plus of A. This will be the limit as epsilon tends to 0 of mu of A epsilon minus A divided by epsilon, where A epsilon is the epsilon neighborhood. Je sais pas comment ça s'écrit, neighborhood of A. So namely, this is the set of points which are at distance less than epsilon from A. Okay, so you have your set A, you enlarge it a bit by some epsilon. Then you subtract A, so you're left with this. And you take the measure of this, and you take the limit as epsilon tends to 0, and I will call that the perimeter. Okay, so this is called the isoperimetric problem. So in general, maybe some examples. Okay, the exact solution of the isoperimetric problem is only known in some very specific cases. So typically the sphere with a geodesic distance, so spherical caps. So spherical caps. This is a spherical cap is just if you want a ball for the geodesic distance. So geodesic ball are the solution. Okay, so if this is a sphere, so a cap will probably look like this. And what I'm saying is that if I take a set A, which has the same measure, yeah, I said okay. Sphere with the geodesic distance, and of course I didn't say, but the R measure, which I normalize to be a probability measure. If I take a set A which has the same measure as a geodesic ball, then the perimeter will be larger for the set A. Okay, this is usually attributed to Paul Levy. I think maybe 1920s, 20-something. Okay, 1920s. So the second case where I know the answer is Rn with the Gaussian measure. And this time the solution is given by affine half spaces. Half space. So again, maybe let me state explicitly. So if this is a set in R2, and if it has the same measure as some space H, then the perimeter of A will be larger than that of H. Okay? So you can formulate this. So for the perimeter of H, you have an explicit formula. Well, here also you have an explicit formula, but somehow I don't remember it. And I can reformulate this as so this will be the Gaussian measure. So this is the perimeter of A. Is at least the perimeter of H, and this will be where phi of x is the Gaussian density. And capital phi is the Gaussian repartition distribution function. So this is the antiderivative of this guy. Okay, so in general, apart from these very specific cases, it is completely hopeless to solve completely the isoperimetric problem. So you want to so you want to so we will content ourselves with like a more modest task, which is finding a lower bound on the isoperimetric. Well, qu'est-ce qu'il y a? You want another example? Okay, so Lehec measure also which is more classical, but somehow here I will focus on the case where my reference measure is a probability measure. Okay. So yeah, the answer is no. I don't want. So in general, this is hopeless. So we want more modest task. So lower bound on nu plus A in terms of okay. When this lower bound is linear, we say that we have a Curie inequality. Okay, so maybe let me write it more formally, definition. So I say mu satisfies Curie if for every set A, mu plus of A is at least, okay, there will be some constant that depends on mu, times, okay, so okay, this is, so of course, if you take a very large set, then you have to take into account that the complement will be small. So it will be the minimum between mu of A and 1 minus mu of A. Okay, this is the... and moreover, I will give a name to the base constant. So the base constant it's called the Curie constant. And I will denote it psi of mu. Okay, so far so good. Okay, what I want to tell you to start with is maybe some connection with Poincaré inequality that we saw this morning. Okay, the Curie can be seen as an L1 Poincaré inequality. Maybe let me formulate this as a proposition. Okay, so it's equivalent. So Curie, so mu. Okay, mu of A 1 minus mu of A less than C mu plus of A. This is completely equivalent. So for every set A. To the following statement. So infimum, well, this is actually a minimum. Minimum C R of integral f minus c d mu set x less than a constant integral grad f at x for every f which say Lipschitz. Maybe some comments on this. Ah oui, lui il monte pas, c'est ça. Ok. Yeah, okay, so then I will, okay, you won't see the inequality. So let me comment now. So you see this is exactly Poincaré, except that for Poincaré you had a 2 here and a 2 here, okay? Yeah, sure. Yeah, okay, I will. Okay, first of all, this was just for show off. You know, it's actually I will only work on Rn, but the statement is correct on let's say, well, maybe not a general metric space, but so here, which is on the inequality that's behind this blackboard, by grad f at x. Sorry? No, I cannot show, this is the point, I cannot show the board. Board number 3 doesn't move. I can rewrite the inequality. Okay, maybe first comment. It's an exercise to see that this is minimal when C is a median for F. So a median means mu of F. Okay, any real number such that those two inequalities are true. The second comment, so here, grad f of x, you can think of it as the lim sup, the local Lipschitz constant, if you want. So this probably makes sense on a metric space that doesn't have isolated points. Okay. Anyway, I will only work on Rn here. Okay, maybe a proof sketch of this. So what's the? So it's not a proof. Okay, it's. Okay, to go from Chigger to this inequality, you need something called the co-area formula. Which is the following. It said that if F is Lipschitz, then, so let me think. So integral on R of the mu plus, so the perimeter of F larger than t dt is upper bounded by integral grad F. Okay, so co-area formula. So usually this is, okay, under some mild hypothesis, this is actually an equality. But here I only need the inequality, and the inequality is somewhat easier to prove. You have soft proof of this. So maybe I can give you a reference where you'll have the details about this. So there's a paper by Udre and Bobkov where they explain very well all this. Okay, so all I'm saying is that here you don't really need fancy geometric measure stuff theory. You have soft proof of this for this inequality. And then here you lower bound this term by using Chigger. Okay, so this will be times the and then you see that the median enters the picture, and then and so on. Okay. And for the converse direction, je me suis pas très bien pris là, non. So conversely, so you apply the L1 Poincaré to a Lipschitz approximation of indicator of A. Like typically f sub n of x is, I don't know, 1 minus n distance from x to A, positive part. Okay, I say typically because actually it's, if you choose exactly that, it doesn't quite work, but like some variation on this will work. So again, I refer the details you can find in Bobkov-Udre. Okay, from this, yes, sure. No, for
in a set you have to be careful. I mean, if you're in an Euclidean setting, you need to work with sets of finite perimeter, but here you're defining the perimeter with a totally negative. There is no like piège.
No, I think it's fine. I mean, I think if I have a very wild set, like the perimeter will be infinite anyway, so the inequality is fine. I think, okay. Here I don't want to enter too much into the details of this, into the specifics, but I don't think I need any more. I don't think I have hidden some hypothesis. I think as it is, it's true.
Because already in this case, if you took like A to be something like a dense effect with like separable.
So here I'm for the converse inequality, okay? So my goal is to say mu plus of A is bigger than C mu of A, 1 minus mu of A. So first of all, if mu a bar, so a bar would be the comment on appelle ça en anglais? The closure, yes, merci. If this is positive, then obviously mu plus of a is plus infinity, and then the inequality is true. So you know, I think you were concerned about sets like that. So for the inequalities, I just I can discard them. So once you have this sort of L1 Poincaré version of Chigger, it's not so hard to see that actually the L1 Poincaré is stronger than the L2 Poincaré. So Chigger. So this is a result of Chigger, by the way. So it's maybe 70 something. So Chigger inequality implies Poincaré. And it's so this would be the qualitative statement, and there is a quantitative statement actually that and moreover so the Poincaré constant. So I'm sticking to Boas' notation. So this is Poincaré constant is less than 4 times the Chigger constant mu with a square. Maybe a comment on homogeneity remark. So about homogeneity. So Cp of mu, so okay, homogeneity, so I will scale everything, so I better be on Rn, maybe this, here, so on Rn. Cp of mu is 2 homogeneous. I mean, if I scale mu by a factor, then Cp is multiplied by lambda square. The Chigger constant, it's 1 homogeneous. So maybe I should have chosen my my notation better, that everyone has the same homogeneity, but somehow I'm used to this, so I can't change. Maybe let me also, like this is the beginning, so let me also give like a proof sketch of this. C'est quel tableau celui-là? Okay, so again, this will be like a sort of proof. Yeah, maybe it will be a bit more serious than the other proof, but so let f be a Lipschitz function. Maybe unbounded for just to be on the safe side. Okay, I can always assume I can translate f if I want. So I'm assuming Chigger and I want Poincaré. Okay, I can always translate it. So let's assume f as its as a median at 0, or that 0 is a median for f. Yeah, now the trick is to apply Chigger not to f, but to the positive part of f squared. Then 0 is also a median for f plus squared. So integral f plus squared. So if I'm assuming Chigger is less than psi of mu, integral grad f plus squared which is 2 psi of mu integral f plus grad f plus. Then you do Cauchy-Schwarz. Okay, so Cauchy-Schwarz here at this stage, so you will get the same term here, but with the power 1/2. So you get integral f plus squared d mu is less than, so you'll have to square this, so you will have 4 psi of mu squared. Integral grad f plus squared d mu, so that's 4 psi mu squared integral. And this is actually grad f squared indicator that f is positive. And then obviously you do the same thing with f minus, and you add up the two, and you get okay. Okay, so Chigger inequality is a stronger inequality than Poincaré in general. Okay, the converse is false. Okay, the converse is false. So I don't have like a counter example handy, but you can cook up example on the line.
You need to somehow
Yeah, there are some technical details that I don't want to. No, I think it's okay because this gradient here is like a local Lipschitz constant. So I think this equality is fine. Maybe. So you have counter example on just on the line, but there is an important result of Boozer says that among the class of log concave measures, which we've seen this morning, the converse is true in a quantitative way for mu log concave. The Chigger constant is less than some constants times the Poincaré constant, where this is universal. So we've had the discussion of what's an universal constant already. Okay, so
you're still on the line?
no, it's true on Rn.
You need a Pierre.
Yeah, sorry. In any dimension. So I want to discuss a bit these Boozer results, and actually I will show you that much more is true than just this. So okay, so for log concave, psi of mu square is more or less the same as Cp of mu. So I will use like this awful notation here to say that the ratio between the left-hand side and the right-hand side is bounded above and below by some universal constant. Okay, you can think of this means the ratio between this and this is between 1/10 and 10. And maybe sometimes you have to put 100 and not 10, but usually 10 is okay. Okay. I want to say a few words about these Boozer results. And for that, I need to introduce some semigroup tools. Okay, so suppose mu is a measure on Rn. So I will assume that, let's say, that mu is supported on the whole space, and this potential, and that the potential V is smooth. Okay, so I will define the Laplace operator associated to mu. Is we'll denote it L sub mu. So if it's applied to some function f, like some smooth function, so you take the usual Laplacian, and then there's a correction due to the potential, which is grad v dot grad f. For f, say smooth and compactly supported. This is a symmetric operator. Meaning that you have some integration by parts. So integrating by parts. We see that integral of L mu f g d mu is minus integral grad f grad g d mu, at least for such functions, smooth and compactly supported. Okay, it turns out that yeah, also in particular, note that so it's minus. And so L mu is monotone and negative. Okay, it turns out that okay, under some technical hypothesis, L mu is what is called essentially self-adjoint. So in a sense, like the minimal extension that you can make of L mu turns it into a self-adjoint. Yes?
What do you call monotone?
Monotone is the fact that, yeah, sorry. It's essentially self-adjoint in the sense that the minimal extension of L mu is self-adjoint. And so I still call L mu this self-adjoint extension. And then I have the spectral theorem. Which tells me that I can write L mu as some integral over a spectral projection. So minus integral from 0 to infinity E lambda d E lambda. So this is like some increasing family of orthogonal projection. So in most situations, I don't want to again, I don't want to spend too much time on this spectral theory because this will not play so much of a role later. Putain, j'arrive pas du tout avec ces trucs. Actually, in most situations, the spectrum of L mu is discrete, and so you can you have a simpler version. I mean, it's most of the time it doesn't make much of a sense, but the spectrum is discrete, and you have like an orthonormal family of eigenvectors, so you can write L mu is minus some very long I don't know if I well like this is the no maybe F is not a good name. You're right. Anyways, yes.
Can you give some intuition what this operator is motivated for when it's doing?
Yeah, it will. So no again.
What is the motivation behind this operator? What does it actually?
Okay. The motivation. So why it is natural to consider it? So L mu, yeah, maybe I should have said it, is no. Okay, the motivation is the fact that it's symmetric in L2 of mu. Okay, is that so? I didn't prove this formula. I left it as an exercise. So the motivation is the fact that, yeah, if you want, yeah, that's what I meant. So it's L mu is the, yeah, this formula is the motivation, really. Like that.
You would say that Poincaré is related to the spectrum of this operator.
Yeah, okay, I won't. Yeah, it will be mostly Boaz will talk about this tomorrow, or maybe the day after tomorrow. But okay, from this formula here, so you have so 0 is an eigenvalue. Is a simple eigenvalue. And the eigenspace is constant function. Okay, constant function. And the Poincaré inequality is equivalent to spectral gap. Namely, there exists some interval such that there is no spectrum between 0 in 0 epsilon. And this is there are more to it. I mean, moreover, the smallest such epsilon is 1 over the spectral gap. Is 1 over the Poincaré constant. So yeah, the smallest will be 0 probably. The largest such epsilon is 1 over the Poincaré constant. So the actually I won't use this here, at least not today. But this this operator is really related to Poincaré. So, for instance, in the Gaussian case that Boaz mentioned this morning, so the Poincaré constant is 1, and actually you can describe the whole spectrum of this operator. So this operator is called Orstadt-Uhlenbeck. And as Bo has said this morning, the eigenspace is the orthonormal basis is given by the Hermite polynomials. So the spectrum is actually just the integers. So you can decompose everything. So everything is more or less explicit. And then what he said about like low degree polynomial satisfies reverse Poincaré and such, you can just read it from this formula. Okay, so what I want to tell you a bit about is the notion of the associated semigroup. Okay, consider the semigroup. So I will denote it PT. So it's really some PT of mu. Okay, it depends on mu, which is ET mu. Okay, so because since L is negative, this is like a bounded operator on L2 mu. So bounded and self-adjoint. Of mu. And what I want to stress now is that there is a probabilistic interpretation. Of this semigroup, and which is the following. So the probabilistic interpretation is that actually this operator is a Markov semigroup, which means it's the semigroup associated to some diffusion process. Okay. So let WT be the standard Brownian motion on Rn, and consider the stochastic differential equation. dxt equals square root 2 dBt minus grad V at xt dt. And then the link between this object and this semigroup is just that for any test function PTF of x is the expectation starting from x of f at point xt. Okay, and this little x at in this index little x means okay, if you want this, when the process is when you initiate the stochastic differential equation at point x. Ah ouais, je sais pourquoi, ouais. Okay, this will be probably and okay, kind of proof. So there are some details that are missing here, but by Ito, if f is nice enough, you will see that when you the Ito derivative at f at xt, it will give you, so you will have you have some gradients. So okay, so you have, so Ito formula tells you that this is grad f at xt times the derivative of your process xt. So the derivative, you will have this martingale part minus grad v at xt dt. And then from Ito's formula, you have also like a second order term that comes from this, this w here, which is given by half the Laplacian. And okay, it's half the Laplacian, but there is this square root 2 here that gives you 2, so this is why I put the square root 2. So if you want this, it's 2 over 2 Laplacian f xt dt. And if you take expectation and so taking expectation, maybe I can write it this way: df of xt is like some martingale part plus this L mu of f at xt dt. Okay, so if you take expectation, we get d over dt. Let's say I'll only do it at t equals 0. And I'll get L mu f at x. Okay, so this somehow shows that this the semi-group associated to this diffusion here is the same as the semi-group e to the t L mu. Now, this probabilistic vision of the semi-group allows you to prove things about this semi-group using probabilistic methods. So let me give you a first example of such an estimate, which is kind of like the easiest thing you could do in that framework. So far I didn't assume mu to be log concave. So let's assume some concavity, log concavity for mu, which amounts to convexity for the potential V. And you can write it this way: if V is okay, if mu is log concave, then Lipschitz function are preserved along the semi-group. Along the semi-group. So here, what I mean is that so for every Lipschitz f and for every time t, the Lipschitz constant of PTF is less than the Lipschitz constant of f. Okay, let me give you the proof. So the proof goes by some coupling argument. So we use a coupling argument. which means that xt, we use some notation. I will put some x as an exponent here to express that I start from x. So x0x is x, dxtx equals square root 2 pwt minus grad v dt. And define xty similarly. And then here, let me emphasize the fact that I use the same Bourgain motion. So okay, this diffusion, you see, it's like a gradient descent, except that you also noise. Okay, and here I start from x and I start from y, but I use the same noise. So this is a coupling argument. And then if you look at the derivative for the difference between the two processes, then the Brownian part cancels out. So you get minus grad v at xtx. Okay, so the key point is that the Brownian part cancels out. And now if you ouais, encore une fois, ça tombe mal. Bon, tant pis. So if you look at the derivative of the Euclidean norm squared between the two processes, you will get a minus and this quantity here is non-negative if V is convex. And so this quantity xtx minus xty is decreasing or non-increasing. And I mean, this is a random process, but it's almost surely non-increasing. And now you're done, because if f is a Lipschitz function, then PTF at x minus PTF at y. By definition, is the expectation of f at xtx minus f at xty. Now you take the absolute value. And this is smaller. then the expectation f x minus f x dy. Which is smaller than the Lipschitz constant of f times the expectation times the, okay, so this is less than the Lipschitz constant of f times the distance between these two guys. But because of this property here, this process is almost surely non-increasing, so also the expectation is non-increasing. Okay, and so you have this for every x and y, so indeed you get which is the result. So of course, like this is a very, I mean, I specify to the log concave case, but if you have some like other convexity property of V, like being uniformly convex or semi-convex, then you will get some information that will depend on your modulus of convexity, of course. Okay. Maybe it's a good point to make a break. Yeah. I don't know. 10 minutes? 5? 10?